Hi everyone, welcome back to this video. In this session, we will study the perceptron learning rule. By the end of this video, you will be able to learn the key steps for perceptron learning, including how to detect misclassified points and how to update the plane by adjusting its weights and bias values. I will also provide graphical interpretation of the perceptron learning rule and show you how the unified learning algorithm is derived. Finally, I will also introduce a hyperparameter called learning rate, which is a speed-accuracy trade-off. In the last session, we have learned the computational modeling of the perceptron and showed its superiority over the NP neuron in 3 aspects. In this session, we will concentrate on the last advantage of the perceptron, that is, its learning ability to update the weights and threshold values automatically. I will first give you a high-level description of the main steps for perceptron learning process, and then provide details for each step. Given a set of labeled data points, the goal of training a perceptron is to identify its weights and threshold values, such that these data points can be correctly classified by the perceptron. We have learned that a perceptron is a binary classifier. Thus, graphically, training the perceptron is to find the plane to separate the labeled data points into 2 groups, where the coefficients of the plane are determined by adjusting the weights and threshold value. Initially, we randomly choose the weights and threshold value W and B to create a plane W times X plus B equals 0. In 2-dimensional case, the plane is a blue line. Above this line is the positive region, showing light blue color. Next, we are going to detect if there exists any misclassified node. That is, to check if any green points outside the blue region, or any red points inside the blue region. In this example, we see that these green points are correctly classified as they are in the blue region, and all the red points are correctly classified as they are outside the blue region. There is only one green point outside the blue region, which is a misclassified point. For any misclassified point, we need to update the plane by adjusting the weights and threshold value W and B. After that, we need to recheck if there exists any misclassified points. In this example, we can see that all the green points are within the blue region, and there is only one red point inside the region, which is misclassified as green. Then, we again update the plane to exclude this point from the blue region by adjusting the weights and threshold value, and recheck the existence of any other misclassified node. In this case, there are no misclassified points. Therefore, we exit for loop and output the weights and threshold value for the final plane. This is the basic step for training the weights and the threshold values for the perceptron. Throughout the learning process, we see that there are 2 steps which are very important. One is how to detect if there exists any misclassified node. The other is how to adjust the weights and the threshold value to update the plane. Let's first look at the detection of misclassified points. Before detailing the detection method, let's first revisit some geometry. Given a straight line in 2 dimensions or a plane in 3 dimensions, we can represent it in a vector form w times x plus b equals 0. Here, w is a norm vector which is perpendicular to the plane. For example, given a straight line y equals minus 2 times x plus 2. To get its norm vector w, we first rearrange the terms as 2x plus y minus 2 equals 0. Then, we put x and y's coefficients 2 and 1 together, which produces the norm vector w. It is perpendicular to the line. If we set the vector x is x and y and b is minus 2, then the straight line will take the form w times x plus b equals 0. Another example is in three-dimensional case, where the given equation 2x plus 3y plus 4z minus 1 equals 0 is a plane. We put x, y, and z coefficients together to make w, which is 2, 3, 4. This is a norm vector perpendicular to the blue plane. If we set vector x to x, y, z and b to minus 1, then the plane also takes the form wx plus b equals 0. Next, let's revisit the relationship between the dot product and the angle of two vectors. Given two vectors a and b, if the angle of AB is 90 degrees, then their dot product is 0. If their angle is less than 90 degrees, their dot product is positive. Otherwise, if their angle is larger than 90 degrees and less than 180 degrees, their dot product is negative. These results indicate that we can use whether the dot product is positive, negative, or 0 to evaluate whether the angle of two vectors is acute, obtuse, or right, respectively. The correctness of the above results can be derived from the dot product definition, where A dot B is defined as the magnitude of A times magnitude of B times cosine theta. Here, theta is the angle between A and B. Since A and B are two non-zero vectors, their magnitude is always positive. Therefore, whether A dot B is positive, 0, or negative depends on the cosine theta value. We can see from the cosine graph that when theta is between 0 and 90 degrees, cosine theta is positive. When theta is exactly 90 degrees, the value of cosine theta is 0. When theta varies from 90 degrees to 180 degrees, the value of cosine theta becomes negative. This validates our above results. Based on this mathematical knowledge, next I will introduce how to determine whether a given point is inside the positive blue region. Given a plane equation wx plus b equals 0, for ease of our presentation, we first assume b equals 0, and w and x are in two dimensions. In this case, w times x equals 0 is a straight line across 0 point. The positive blue region is above this line, in which any point x satisfies w times x greater than or equal to 0. Thus, if the given point v is inside the blue region, v must satisfy w times v larger than or equal to 0. Otherwise, if v is outside the region, w times v is less than 0. In this example, v is inside the blue region. Thus, w dot product v is non-negative. The non-negative dot product implies that the angle between W and V is less than or equal to 90 degrees. Using the above result, let's take an example. Given the line y equals minus 2x, the positive region is above this line, showing light blue color. Given a point V, 1, 3, to determine whether V is inside the blue region, we first rewrite the equation into the standard form. We notice x and y's coefficients are 2 and 1, which makes the normal vector w of this line. Since the given point V is 1, 3, then we calculate their product to see if it is negative or positive. Since the result of this product is 5, which is positive, therefore V is inside the blue region. This is consistent with the fact that the angle between the vector W and V is less than 90 degrees. We next consider the case when B is not 0. In this case, the line is not across the 0 point. Given a point V, to determine whether V is inside the blue region, we can use a similar approach. If V satisfies W times V plus B is greater than or equal to 0, then V is inside the region, otherwise outside. However, in this case, we cannot simply use the angle between V and W to determine if V is inside the blue region. Even if the angle between V and W is less than 90 degrees, there are still chances that V may be outside the blue region, because the blue line is not across the 0 point. To address this problem, when the plane is not across the 0 point, we can use a high-dimensional space to represent this plane, to make the plane across the 0 point in high dimension. To be more specific, we now introduce two transformations in mathematics. One is affine transformation, the other is a linear transformation. If the line wx plus b equals 0 is not across the 0 point, we call it affine transformation. Otherwise, the line is across the 0 point, which becomes w times x equals 0. We call it linear transformation. It is important to note that any affine transformation in n dimension can be converted to a linear transformation in n plus 1 dimension. We can see in the linear transformation, the last element in the vector x is 1. We now replace this one element with another variable, xn plus 1, and we let xn plus 1 equals 1. This equation denotes a plane, and w times x equals 0 denotes another plane. We notice that the intersection of these two planes in n plus 1 dimension is exactly the line in n dimension. Therefore, for binary classification problem, if the decision boundary w times x plus b equals 0 is not across the 0 point in n dimension, we can convert it into a plane w times x equals 0 that is across the 0 point in n plus 1 dimension. To explain this more clearly, let's take an example. Given a data point v and a line in 2 dimensions, we want to determine if v is above this line. Since this line is not across the 0 point, we cannot simply use the angle between the vector v and w to determine if v is above the line. However, if we convert this line into 3 dimensions, it will become a plane that is across the 0 point. Specifically, we can add an element b into the vector w and an element 1 into the vector x. Then, the line takes the form w times x equals 0 in 3 dimensions. In the vector x, we replace the last element 1 with x3 and add another equation x3 equals 1. As a result, the red line in 2 dimension becomes the intersection of the two planes in 3 dimension. Now let's visualize these two planes in 3 dimension. The plane x3 equals 1 is shown in blue color, which is parallel to the plane spanned by x1 and x2. We can project the red line at the given point V onto this blue plane. W times x equals 0 denotes another plane shown in red color, which is across the 0 point in 3 dimension. The norm vector of this red plane is denoted by W, which takes the value W1, W2, and B. It is important to notice that in 2 dimension, we use a red line for binary classification, and the red line may not cross the 0 point. When converted to 3 dimension, we can use this red plane for binary classification, and this red plane is across the 0 point in 3 dimension. From this example, we can clearly see that in the 2-dimensional blue plane, V is above the red line, and this is equivalent to the fact that in 3 dimension, V is below the red plane. When using the red plane in 3 dimension as a classifier, we can use the angle between its norm vector W and the data point V to determine if V is above the line. Based on the above discussion, we can use the expression W times x equals 0 to represent a plane. Here, the vector W may contain both weights and bias value. For an ideal classification, we expect all the green points are inside the blue region. That is, the angle between each data point vector V and W is less than 90 degrees. Ideally, red points V should be outside the blue region, satisfying the angle between W and the red V is larger than 90 degrees. However, in this example, there is a misclassified point, V5. Therefore, we are going to train the plane by adjusting its coefficient, W. We next study how to update the plane by adjusting the weights and biased values. To show the learning rules for perceptron, let's first revisit 2 vector operations. Given 2 vectors A and B, their vector sum A plus B is obtained by connecting A's head to B's tail and drawing the vector from A's tail to B's head. This follows the parallelogram law. Similarly, A minus B is obtained by drawing the vector from B's head to A's head. Based on these 2 vector operations, now let's see how to train the perceptron. In this example, we notice that the green point V5 is misclassified as red, which is outside the blue region, indicating that the angle between the vector V5 and W is larger than 90 degrees. In this case, when a positive data point is misclassified as negative, we use the following rule to update W. That is, W new equals W old plus V. In this example, to update W, we add the current W and the V5 together, which produces a new vector W in purple color. We then rotate the plane to make the line perpendicular to the purple vector. After rotation, we see that all the green points are inside the blue region. However, there is another red point, V6, whose value is 0 but is misclassified as positive in the blue region. In this case, the angle between vector V6 and W is less than 90 degrees. To exclude V6 out of the blue region, we use the minus learning rule. That is, W new equals W old minus V. Then a new vector W is produced, showing purple color. Based on this new vector, we rotate the line to make it self-perpendicular to the purple vector. After update, we notice that all red points are outside the region, and all green points are inside. There are no points misclassified. Thus, the learning process is complete. Based on the above example, let's now summarize the learning rules for perceptron. Firstly, we initialize W at random to create a plane. When there exists any misclassified input V, the following loop begins. If V is positive but misclassified as negative, that is, the angle between the vector W and V is larger than 90 degrees, then we use plus learning rule. We add V to old W to get new W. Otherwise, if V is negative but misclassified as positive, that is, the angle between vector W and V is less than or equal to 90 degrees, then we use minus learning rule. We subtract V from old W to get new W. The above loop continues till there are no misclassified points. It is important to note that the above learning process can be simplified further by merging the above two cases together. This is because, in case 1, plus V can be rewritten as plus 1 times V. Here, 1 can be regarded as the actual value 1 minus the predicted value 0. Similarly, in case 2, minus V can be rewritten as plus minus 1 times V. Here, minus 1 can be regarded as the actual value 0 minus the predicted value 1. In both cases, we notice that these parts are the actual value of the data points, whereas these parts are the predicted value of the data points from the perceptron. Therefore, these two cases can be merged in a unified manner as actual value minus predicted value. Consequently, we can simply use a single equation to describe the aforementioned two cases. To be precise, we use y of v to denote the actual value of v, and y hat of v to denote its predicted value. Here, the values of yv and y hat v are 0 or 1. Then, the learning rule can be described as follows. New w equals old w plus the difference between actual and predicted value multiplied by v. In practice, we often put a small positive factor, alpha, in front of the difference. Here, alpha is called a learning rate, whose value is user-specified, which is between 0 and 1. Alpha is a configurable hyperparameter. We introduce the alpha because it determines the step size at each iteration in the training, which is a speed-accuracy trade-off. If alpha is set to be smaller, it will take more training iterations, leading to slow convergence rate. In contrast, larger alpha will result in rapid changes that may make the learning jump over the optimal solution. Here is an example which shows the effect of different learning rate alpha. When alpha is set to 1, the step size becomes so large that it may make the learning jump over the optimal solution. Therefore, the blue region would rotate too much and include even the red point. In comparison, when alpha is set to 0.1, this will make the blue region rotate mildly by taking small steps, so that it would not include the red point. That's all for today's session. Thank you for your watching. Bye.